John Chaika from the University of Utah, who will be talking about his beautiful theory.
First off, thanks to the organizers for inviting me and organizing such a great conference with so many great talks. So I'm going to be talking today about interval exchange transformations and flows on flat surfaces, a subject I like a lot. And in particular, I'm going to be talking about the isomorphism problem and another thing called disjointness, which I'll introduce. And so the basic idea is, typically, does it happen that for some strange reason, most Ayitis are actually all the same? I don't know. Okay. So before going into interval exchange transformations, let's start with rotations of the circle. So let's just think about the unit circle in the complex plane and think of a very simple isometry on it. You just take it and rigidly rotate it by an alphath proportion of its circumference. Okay. So that's the map that's given there, and I guess I'm assuming x is between 0 and 1. And so it's just rigidly rotating by an alphath proportion of its circumference. But we can, instead of thinking about this in the, you could just think about x and forget about the e to the 2 pi I. And this is very similar to just a map of the 0-1 interval to itself. Given by shifting everything over by alpha, well, then you might leave the 0-1 interval. So just subtract off the integer part. So this is just x plus alpha modulo 1. Makes sense. So this is one of the first introduced and best understood dynamical systems. And it shows up in a variety of ways. I'll mention one of them. So you can also take the square torus and hit it by this particular element, 1 alpha 0 1. You get some other torus with a nice flat metric on it. And opposite sides are identified. And so you could just consider flowing straight up on this. Okay, so we just flow straight upwards. And so you get that. You reach the top, and then you move over back to the bottom. And then you hit the side, and you move back over to the top and repeat. And so this is a map of the torus on the torus. It's a flow on the torus. But maybe you're like me, and 2 dimensions is much too hard. And you prefer 1 dimension. 1 dimension, something nice. And so since I'm just flowing by a straight line flow till I get to the top, and I don't have any other identifications, maybe I just want to think about what this is doing on the bottom. Where this blue line that starts at some place on the bottom next crosses the bottom. And that gives me some dynamical system just on the bottom. This is called the first return map for obvious reasons, which are that you start on a point in a set, and then you just map it to where it first returns to that set. Okay? And so if you look at that, that's going to give you rotation by minus alpha, okay? Where the alpha here is the same as the alpha on top. Okay? So this is a way that rotations show up. Okay? So rotations have 2 kind of basic different types. There's rational rotations and irrational rotations. Rational rotations, each point has only finitely many points in its orbit, then it comes back to where it started and repeats it. The number of things in the denominator when it's written in least terms. And otherwise, you're irrational. And it turns out that if you're irrational, the orbit of every point will be dense. And even more, it distributes the right amount in any interval. So if you ask how many times it asymptotically lands in the interval from 0 to 1/2, it's half of the time. And there's nothing special about the interval from 0 to 1/2. It's for any interval. It hits it as often as it should, which is the length. And so this is called unique ergodicity. And in our context, this is equivalent to the fact that if you want special measures, which are probability measures, in which when you push them forward under the dynamics, you get back the same measure you started with. These are called preserved measures, because pushing them forward keeps them the same. Then there's only one of these, only one such probability measure, and in this case, it's Lebesgue measure. Okay? And so in ergodic theory, you usually have descriptions of almost every orbit with respect to any ergodic measures you have. But unique ergodicity in our context is wonderful because you get descriptions of every single orbit. And this is a very special thing, and a very nice thing. So we know how every point travels through the space, at least coarsely, as in how many times it'll hit a given interval. Okay? So any questions on this? Okay, so now we can talk about the isomorphism problem. And so what does the isomorphism problem ask? So we're given 2 dynamical systems, T x mu and S y nu. T maps the space X to itself, and S maps the space Y to itself. T preserves mu, and S preserves nu. And the question is, when are they actually the same? So what does the same mean? So if they're the same, it means that you have we have X and X here, and we have Y and Y here. And I'm moving across by X, by T. Here I'm moving across by Y, by S. And when they're the same, it means that if I have a map phi that makes this thing commute, and it also has an inverse that also makes it commute, and pushes forward the measure mu to nu, and pushes forward the measure nu to mu. So I think a picture is much more helpful than the definition, which is written up there. So the point is, phi should be bijective, bimeasure preserving, and push forward mu to nu, and therefore it also pushes nu to mu because it's bijective. And this is in measure category, so we only care about things almost everywhere. I don't care if on a set of measure 0, but in the setting of rotations, everything is super nice. And so it turns out that the isomorphism problem is completely solved for irrational rotations. So we're wondering when two rotations are isomorphic, and this problem is completely solved. It was solved in 1942 by Helmholtz and von Neumann. And so it's only in the obvious case. There's no secret ways that rotations that look like they shouldn't be the same are actually the same. So you could either be alpha, something's isomorphic to itself, that's no surprise, or minus alpha. And it's not hard to see that conjugating by minus the identity is the isomorphism in this case. So that's a great thing. We've completely solved the problem. Yay. Just a brief remark on their methods. They're spectral, and it works for systems that have discrete spectrum. And it's not hard to see that rotations have an orthonormal basis of L2 given by eigenfunctions. So the spectrum is purely discrete. And this has enabled them to get a classification of when two systems with discrete spectrum are, well, conjugate, but in our setting, isomorphic. Okay, so, and in particular, so you have a map of the space 0, 1 to itself, and it preserves Lebesgue measure. So it acts as an isometry on L2 of lambda, of the unit interval. Now it turns out it's invertible, so it's actually unitary, and you can look at the spectrum. And in our case, it's discrete pure point spectrum, and that's how they come up with their classification. So any questions on rotations or anything like that? Because I'm about to move on to IETs. Great. Okay. So here's the definition of an IET. What do? You take an interval and you chop it up into d pieces of different lengths. So the lengths are L1 out to LD. And the third interval starts where the second interval ended. So that's the idea behind this. And then you exchange them according to an order. So your point lies in some interval, and you subtract off the intervals that started before it, and you move in all of the intervals that are sent before it by a permutation. Okay, so that's the definition. And as is often the case, a picture is worth at least 1,000 words. So I'm drawing you a picture of an interval exchange transformation. The colors so I'm chopping the interval I care about into 3 pieces, blue, red, and black. And I'll exchange them according to the order 3 goes first, then comes second, and then comes first. So that's the order I'm doing. And so let's see what happens. Okay, so the black piece gets sent to the beginning, the blue piece gets sent to the end, and the red piece gets shifted over by the difference in length between the third and first interval. It's not hard to see that from this, that you would, if x was in the second interval, you would subtract off the first interval. The only thing less than 2 is 1. And then you'd add to it what's sent before it, the 3. So, because 2 gets sent to 2, 3 gets sent to 1. Okay. And when you cut again, this is a dynamical system. We cut according to the same rule we previously had. So we cut in the same places, and things get split up even more. Okay. So the end of red and all of blue gets sent to the beginning, right? Because that's underneath where black was. Okay, at the beginning. So that's an interval exchange transformation. And let's say a few words about them. These are nice systems. So first off, they generalize rotations. Why did I start talking about rotations? because they are the simplest interval exchange transformation. They're interval exchange transformations of two intervals. And so their lengths are, so I need to tell you the permutation. Well, that's not very hard. If it was 1, 2, it would be the identity. So it's 2 goes to 1. And the lengths are 1 minus alpha and alpha. So the n piece gets pushed over by alpha. It goes to the interval from 1 to 2. You subtract 1 off because you were doing everything mod 1, and it gets sent to the beginning. The part from 0 to 1 minus alpha gets shifted over by alpha and stays in the interval. And that's how to see that rotations are 2 IETs. So rotations are order-preserving isometries that preserve Lebesgue measure and are really nice systems. Similarly, interval exchange transformations are piecewise isometries. They might actually be discontinuous. It's not hard to see that this picture we saw above actually is discontinuous. And they're piecewise isometries. They're piecewise order-preserving, and they're invertible. So in Mladen's talk, some things that were piecewise isometries but weren't invertible came up. But these are invertible, and that means that they preserve Lebesgue measure. Okay? And their inverse is always also an interval exchange transformation. So these are nice things. They have a lot of nice properties. So you can fix an order on the interval exchange transformation, and then it only is determined by the lengths, by the length vector. Okay? So in the case we saw before, this would be the length of red, the length of blue, and the length of black. That determines the entire dynamics. And you might as well assume that the sum of all of the lengths is equal to 1, because you can always normalize to make this the case by just dividing by the total length, so the sum of all of the intervals. And that doesn't really change the dynamics. So we identify interval exchange transformations with a fixed order, with the simplex of dimension 1 less than the number of the letters sitting in R to the D. Okay, so the standard simplex, because we want all of our length vectors to be non-negative, right? We shouldn't have negative length. And we're having a one-dimensional condition that the sum of things add up to 1, so it's dimension D minus 1. Okay? So what's the important thing about this? This is now a nice Euclidean space. It has a uniform measure on it. It has a metric. You can say words like almost every point in it. And so when we talk about almost every IET, what we think of is a fixed order. And then you identify the IETs with that as the simplex. That's the parametrizing space. And then almost every is almost every point in that parametrizing space, which with respect to the natural D minus 1 dimensional volume. And so there's a great theorem about interval exchange transformations by Mazur and Veitch, which is some analog of Weyl's theorem. And what is it? It's that almost every interval exchange transformation is uniquely ergodic with respect to Lebesgue measure. Okay? So we have exactly what we had in Weyl's theorem, that for almost every rotation, any point falls in an interval as often as it should, proportional to the length of that over the total length of the space. Unlike Weyl's theorem, we don't have a full classification, but that might be a little bit too much to ask. These are not as nice as rotations. They're still very nice, but not as nice. Yeah, and also the only preserved measure is Lebesgue, just as in the other case. I should remark that in the case of rotations, you had a dichotomy. Either the orbit of every point was periodic, or the orbit of every point was uniformly distributed, and you had unique ergodicity. That dichotomy fails for interval exchange transformations, but that's a subject for a different talk. Yeah. Okay, so we talked about how rotations came about from flows on tori. In the same way, interval exchange transformations come about from flows on something else. They come about from flows on Riemann surfaces with some special metric. And what is this special metric? There's a finite number of bad points that aren't so bad. And away from those bad points, the transition functions between charts have to be translations. Okay? And I told you that the bad points shouldn't be so bad. They're, except for they're cone angles of integer multiples of 2 pi. Okay? So I think a picture is often worth 1,000 words. And this is definitely the case here. What we have here is we have a flat surface, and opposite sides are identified. So I've drawn you the chart and the transition functions. So if I cross from here to here, I come back here. If I come here and hit here, I come back over here, come down, and so forth. Okay. Does the picture make sense? Opposite sides are identified, and that's the transition, tells you the transition functions between the charts. So I mentioned this thing about bad points. If you look at this point here has to be the same as this point here, because they're endpoints of the same side. And similarly, it has to be the same point as here. And if you look, all of the corners actually have to be the same point. And you can do an angle calculation. Just go around here, start counting the angles, then come up here and keep counting the angle, and repeat this and keep counting the angle. And you'll get that it's 6 pi. Okay? So that's the exceptional point, which has angle and integer multiple of 2 pi. So this is a genus 2 surface with one singularity of 6 pi. So the charts are translations. And so they preserve orientation and they preserve angles. So you can lift straight lines from the plane to your flat surface, and it makes sense to keep going, unless you land in one of these cone points where then it's unclear which way you should shoot out. Okay? You have several choices of shooting out if you do that. And so there is a well-defined flow in each direction on the flat surface, except at a measure 0 set of points, these ones that land that go from one singularity, that hit a singularity in either direction. Okay, and you get this in every direction. Right? So these flows give us an Ayiti, and I think I will do a proof by showing you pictures. So what can I do? I can start with the bottom and I just flow up. And in this special example, part of the bottom goes all the way up to the top, where it will be identified right back to the bottom. So we're playing the same game we did on the torus. We're fixing one side, we're doing a flow, in this case also in the vertical direction, and sending points on the bottom to where they next cross the bottom. Okay, does that make sense? And in particular, since the bottom and the top are identified, it's also where they cross the top. Okay, so we've got this point on the bottom, the segment on the bottom, and it flows all the way up, and it identifies to the top there. Now, it can't be extended any further because it'll hit this cone point, right, which will have some different identification and send it somewhere else. So what you're seeing already is on a segment that up until a certain point, everything's moving by isometries that are preserving order, right? And at cone points, other things happen. But on these segments, things are moving by order-preserving isometries. Let's look at the next piece. So this is colored in blue. It will be split into 2 different parts in a little bit, but let's first follow it. So it flows up and hits the angled side up top. Okay? And then it gets identified back to the bottom. Now it flows up, and eats up most of that side. Notice the little part that's black on the bottom will fill in the rest of that side. Okay. And then we follow the identification, and it goes over to the other side. Now it flows up, and part of it will go all the way up to the top, which will then be identified in the bottom, and part of it will hit this corner area here. And those will be colored in yellow and green. So now the yellow part has been identified back to the top. The green part hasn't. It hits there, it goes over, and then comes all the way to the end. So the back of blue gets sent to the very front of the interval we started with. Okay. And so just take my word for it, this last black piece comes up, over, and gets over, hits here, comes here, and fills in that last little piece there. Okay. So that's seeing that the vertical flow is giving us an interval exchange transformation. And everything is isometry, and so the identification is in order-preserving isometry, at least piecewise. Okay. So that's the picture. And so just to wrap this up, so here's an interval exchange transformation we see. So the first interval gets sent to the second position. The second interval gets sent to the last position. The third interval gets sent to the first position, and the fourth interval gets sent to the third position. Okay. And so there's also a space of these guys. I could have varied my angles between the sides, right? I could have taken these and I could have moved it a little bit, or I could have stretched and shrinked the length of things, still keeping parallel sides parallel and of the same length, so things are moved in pairs. Okay? And I could get a whole local neighborhood of flat surfaces. Okay? And so this gives us local coordinates on the space, and so it makes sense to talk about almost every flat surface as well. And so Maser and Veach also proved that independently, that for almost every flat surface, the vertical flow is uniquely ergodic. So we have the same statement about pushing forward of a single measure to get back itself, single probability measure, or alternately, you can do the version of intervals. Rather than hitting an interval, we're looking at time spent in a rectangle, and you hit it the right amount. So I'm not assuming these are unit areas, so I want to normalize by the volume of the surface, by the area of the surface. Okay? So that's so those typical things are uniquely ergodic as well. So now we want to consider the isomorphism problem for interval exchange transformations. And so almost every pair of interval exchange transformations are not isomorphic. Similarly to the case of Maser and Veach's theorem generalizing Weil's theorem, there's no longer, this kind of generalizes the Helmholtz-von Neumann theorem, and we also lose a complete classification. But that's somehow, I think, maybe asking a bit much. And moreover, they are disjoint, something I'll define in a moment. And jointly with Vaibhav Gadre, we proved that the same thing is true for vertical flows on almost every flat surface. So if I take one flat surface and I take another flat surface and look at the vertical flows on both of them, chances are they're actually different. There's no measurable map that secretly sends one to the other. And so that the dynamics commute. So I should tell you what this word disjoint means. It's a notion of difference. And so what is it? You want to take two measure-preserving transformations, and you want to consider the product transformation. So our space was X and Y, two separate spaces, but instead we consider the space X cross Y. And on the first coordinate, we move by T, and on the second coordinate, we move by S. Okay? And then we want to look at the systems we see in here. So that's identified by measures that are preserved. Those are the systems. But we want them to somehow have something to do with T and S, so we want them to project to the first coordinate as mu and to the second coordinate as nu. Okay? So that's the idea of a joining between the measures. And you always have one such map. You always have one such measure, and that's the product measure. Product measure always is a preserved measure. And they're disjoint if that's the only one. And so a way to study how systems are interacting is by studying these measures, which are called joinings. And so the product measure is called the trivial joining. Okay? So I should convince you now that this is a notion of two things being different. I said moreover, right? So in particular, this should imply that they're not isomorphic. So I want to convince you about that. Okay? So we have so I want to tell you a space is not disjoint from itself. So the diagonal supports a perfectly good joining, right? And so it's not hard to see that you can look at x comma phi of x, and if t and s are isomorphic, this will be some kind of a diagonal type thing, which will also support a joining of the two. So they can't possibly be disjoint. Does that make sense? So in particular, it applies not isomorphic. But I said moreover, so I should tell you it's more than that. Okay, so you can also ask about factors. So what's a factor? So let's say I drop the condition that this is invertible. And I just want this diagram to commute. And push forward mu to being nu. That's saying that S is a factor of T. And the phi is like the factor map. Okay, it's a kind of simpler thing. You're possibly forgetting some data with phi, and seeing what's left is just S. Okay. Does that make sense what a factor is? Yeah, and you want this diagram to commute. And so if you have a factor, that supports a joining too. So you can look at where you get sent by the factor map and then pull back everything that gets sent there. Now T makes it so that when you apply T to this, it goes to T of x, H inverse H Tx, because the diagram commutes. And so the factor will support a joining that's called kind of also like a bigger diagonal type thing. That should be a phi. Sorry about that. H is phi. Sorry, H is phi. Okay. And so if two transformations have a non-trivial common factor, you can just pull back the factor map on both of them and get a joining between them. So so two things being disjoint implies that they have no common factors. Okay, so they're really different. They don't even have pieces that look the same. Okay? And just a remark that this is a different thing than in the case of rotations, where this problem is also completely classified, because it's very possible for two rotations to be not isomorphic, but still not disjoint. So in particular, if you look at rotation by beta and by rotation by 2 beta, one is a factor of the other. So you can consider the map times 2. So let's do an example here. This will be rotation by beta. This will be rotation by 2 beta. And the map I want to consider is the times 2 map. So what is this times 2 map? So times 2 map of x is going to be 2x mod 1, or minus the integer part of 2x. Okay? And so the distributive property says that that rotation by 2 beta is a factor of rotation by beta by this map. Okay? And clearly they're not isomorphic. But. All right. So there's some consequences of this result. So for almost every pair of interval exchange transformations, T and S, the product is uniquely ergodic with respect to lambda square, with respect to the product of Lebesgue measure. So why is that? Because what your measure projects to better be a preserved measure of T and S. And for the typical Ayiti, there's only one choice by Mazur and Veitch, and that's Lebesgue measure. Now, if you project to the right thing, being disjoint means there's only one choice of that, and that's the product of the two. So that's the only possibility. So this is some kind of version of Mazur-Veitch theorem for the product of two interval exchange transformations. And I should remark that there's nothing special about 2. The product of two interval exchange transformations is disjoint from almost every interval exchange transformation. So the same thing is true for 3 tuples or k tuples. Now, if you think about what if you think about what a product of two interval exchange transformations is, you cut the interval on one of the sides and you cut the interval on the other sides, and then you exchange things. So a box that you're left with will be sent somewhere. So this gives us an example of rectangle exchange transformations. And unfortunately, unlike interval exchange transformations, which you can cut any way you want, and so long as you fix your order, you can send them, and that's a well-defined map. It's not clear you can do this for rectangle exchanges, but you can when they're the product of two IETs, right? Those always give us rectangle exchanges. And so what we get is that the orbit of almost every point is recurrent. And so what does it mean to be a recurrent? It means that under your dynamics, you come back arbitrarily close to yourself. So your distance under it, at least along a subsequence, is tending towards 0, along a subsequence. And why is this? Because you're uniquely ergodic, so you hit every region as often as you should. So if I fix a small ball about a point, this has some small but positive measure. So I have to hit it infinitely often, in fact, the right proportion of times. Okay. And so there's still an open question of Gowers, which is, does every rectangle exchange have the property that every single point is recurrent? So I think it's known, so for interval exchanges, it has been known at least since the 70s that every point is recurrent. And so this is asking for some kind of two-dimensional generalization. Just a remark, I think he says in an article that he suspects the answer is yes, and that other people suspect the answer is no. So that's a question. Yeah. So I should remark that this is still open even for the product of two interval exchange transformations. And a possible place to look for a counterexample would be a pair of IETs that have some kind of crazy joining between each other that might control some orbits. And some orbits might spend time near one measure and near another measure. Okay. Yeah, so I just wanted to stress that it's still open even for the product of two IETs. So I'm going to now tell you a little bit about the method of proof of the fact that two typical interval exchange transformations are different from each other. And so the method of this proof is also spectral. So it relies on a criterion for disjointness due to Frank Hahn and Bill Parry. And Frank Hahn used to be at Yale. He unfortunately died very young. So what are we going to do? We're going to consider L2 functions of integral 0, because constant functions get sent to themselves by measure-preserving maps. So yeah. And so we want some way of saying that two things are disjoint. So this is a notion of difference. So we should have some way of saying that two things are different, and hopefully it's a very robust mechanism, because I have uncountably many objects that I want to somehow distinguish. Okay? So I'm going to use sequences to do that, where one transformation is behaving very differently than the way the other transformation is behaving. So in particular, what I'm requesting is that one of them is converging to the identity in the strong operator topology, or the weak operator topology, while the other one is converging to the 0 operator in the weak operator topology. Okay? So it shouldn't be surprising that that these two things better be very different than each other. These are two very different phenomenons, and this actually implies that they're disjoint. Okay. So, but I don't know if everybody knows what the strong and weak operator topology, or remembers at this late hour of the Saturday. So here's the definition. So what is convergence in the strong operator topology to the identity means? It means if I fix any vector and I start applying the powers to it, this sequence of powers, it's going in L2 to itself. Okay, so the L2 norm is going to 0, okay, just along this sequence, subsequence. So maybe I'll just make a remark. Rotations are definitely not, many rotations are not the identity, but even irrational rotations have powers that converge in the strong operator topology to the identity. So this is not saying that these transformations are the identity or periodic or something. Okay? And then what does it mean to converge to the 0 operator in the weak operator topology? It means if I consider an inner product between two vectors, but one of them I'm pushing by my unitary map along the subsequence, then this is going to 0. Okay? It's what the 0 operator applied to F, comma G would do. Okay? So any questions on that? And so maybe it helps to say these things in words that don't use L2 stuff. So it's also saying that if you, in L1 norm, the function x goes to t to the n sub I of x is converging to the identity function, x goes to x. Right? That's L1 norm there. While in L2 norm, things are getting spread out and mixed. Right? This is like independence, this bottom condition, that the integral of f composed with s to the ni times g is going to the integral of f times the integral of g. Right? So this is some kind of, it's becoming asymptotically independent under the applications of s to the ni. So what does this mean for those who are familiar with dynamics? It means along this sequence, s looks like it's mixing, and along the other sequence, t looks like it's converging to the identity. So maybe from a more dynamical standpoint, that seems like they better be very different. So how do we go about showing that for the typical pair of IETs, I can find a sequence where one is converging in the strong operator topology to the identity, where the other is converging in the weak operator topology to the 0 operator? So fortunately, Wiener's lemma tells us that if you have continuous spectrum, then there's a sequence of density 1 where your Fourier coefficients of your spectral measure converges to 0. Okay? So somehow, if you have continuous spectrum, having sequences, you have lots of sequences that converge to 0 in the weak operator topology. And by work of Avila and Forney, almost every interval exchange transformation has purely continuous spectrum, aside from constant functions. Okay. So what we do is we start out with our transformation S that's weakly mixing, and we get a density 1 sequence where it's converging in the weak operator topology to 0. And so all we need to do for our other transformation t is to find a rigidity sequence in this sequence that's basically all of the natural numbers. And it's missing some, but it's most of them. It's density 1. Should I define what density 1 means? Anyone not know? Okay. Yeah, okay. So then you need to do the next theorem, which is that in any sequence of density 1, almost every interval exchange transformation has a rigidity sequence. So just briefly, the logic of the proof is you pick almost every interval exchange transformation, which is weakly mixing. You get your sequence of density 1 of times where it's converging to 0. And then this density 1 sequence gives you a full measure set of IETs, depending on your sequence, where each such IET can find a sequence where it converges to the identity in the. Okay. So I should remark, it was already known that almost every interval exchange transformation had a sequence where it converged to the identity, and this was proved by Veach. So this is a mild strengthening of a result of Veach. And so, I mean, it's preposterous that it has to be density 1. Any positive density should be more than enough. I don't know how to do this. I think it's a great question. Okay. So we have another question, which is, do circles equidistribute in every flat surface? So what do I mean by this? I mean, I want to start at a point, and I want to flow simultaneously in all directions, but at the same speed. Okay? And so the question is, does this equidistribute? And I don't know about you guys, but I think the answer should be yes. I really do. And so one can play with quantifiers, but I don't know how to do this. And so this is part of work in progress with Pascal Hubert. And we showed that for almost every flat surface, and for any point in that flat surface, it's true. Except we can't say that much. We can't say about all times. We need to toss out a density 0 set of times. So there exists some, on the bottom, this A should have a P underneath it. You have some set of the real numbers of full density so that along times in that you're becoming equidistributed. Okay? And so that means you hit every rectangle as often as you should. Okay? So, yeah, okay, this is written incorrectly. I'm sorry. So what did we show? Yeah, sorry about this. So we showed the following thing. We showed that the integral from 0 to 2 pi of f of you do flat surface flow. So what are we doing? We're flowing in all of the different directions we could, and we're just integrating d theta. We're not integrating dt. And we're taking the limit of t in our special set A sub p. Okay? And this converges to what it should, which is the integral of the function over the measure of the space. Okay? So that's what we, yes?
Did you divide by the length of the circle?
Yes, I did. Yeah, thanks. Yeah, so it suffices to check on continuous functions or rectangles to check for equidistribution. And so this shows that circles equidistribute typically. But maybe some remarks on quantifiers. Unfortunately, this result only holds for a non-explicit set of full measure, completely non-explicit. It also only holds for a density 1 set of times, which is unfortunate. Fortunately, we get it for every point, but those are two remarks on the fact that the quantifiers are far from being optimal. And so how do we go about doing this? So I first claim that it suffices to show that for typical pair n tuples of directions, the flow in those n tuples are uniquely ergodic. Okay? And why is this? So first I should call attention to the fact that this will let me control all orbits. And if we're flowing a point in different directions, we're starting from the same point. So this is describing a measure 0 set in the product of the surfaces. So we really want to control every single point. Okay? But why should, so it's clear we want some kind of control on every single point, but why is this good enough? Well, so by the strong law of large number, if I take a product of my surface with itself n times, where n is some enormous number, and I pick a rectangle, for most points in the product of these surfaces, I'm no longer restricting to the diagonal. So for most points in the product of these surfaces, it's going to hit rectangles as often as it should. And this is just the strong law of large numbers. What's happening in one surface has nothing to do with the others. These are all independent. Okay, does that make sense? Okay, so this is so for a fixed n, this is the set where we hit a rectangle either much more or much less than we should, is some kind of set of very small measure. Okay, the omega should be a q. Sorry about that. Okay. But we are only caring about a measure zero set of points, our p comma dot 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 p. But if we're uniquely ergodic, we control that point too. And it equidistributes in the product of n copies of the flat surface. So you look at your good set, which is the complement of the set. So we have our set here, which is somehow the bad set, the set that spends too much time in our rectangle. And the good set has almost full measure. So under our dynamics, every point spends the vast majority of its time in the good set, not the bad set, because the good set has almost full measure, where the projection is all about the same. And what is this exactly saying? This is exactly a point about flowing at time s in the different directions, your point p, and having them land in the rectangle as often as they should. Right? Does that make sense? So you want to think of the product of many surfaces, and you're flowing in each of them separately, but then you want to project it back down to your original surface and see that your cloud is pretty well distributed. That's the picture. And to prove unique ergodicity, it suffices to show that for any n, and it suffices to prove disjointness. And this is by an inductive argument. You get unique ergodicity of the product, and then you get disjointness of the next one from the previous one, so you get unique ergodicity of now the n tuple of products. And each time you toss out a set of zero measure, but it's only a set of zero measure. And so what we really prove is that for almost every flat surface and any n, for almost every n tuple of directions, the flow is the flow from the first n minus 1, the product of the first n minus 1, is disjoint from the last one. And that's what we prove. And so unfortunately, it's only for almost every flat surface. And I should remark that this doesn't follow by my result with Gadre, because what this is asking is about what's happening on a particular flat surface as you vary directions. So you're only talking about measure zero sets at a given time. So this is some kind of finer result. So any questions on this? So I'll wrap this up by so since you don't have questions, I have some questions for you. And I think some of these are kind of absurdities that we can't answer them, or that I don't know how to answer them. And I think they're great questions. So, so notice I was kicking out a density zero set of times. Even on the flat surfaces I talk about, I don't know what happens off of those density zero set of times. So pick some kind of sparse sequence of times. So I chose n factorial, but just because it's sparse, no other reason. And it has a nice, and you can write it easily. Could it be that for almost every point on your flat surface, it converges to itself under the flow in almost every direction? This somehow is unbelievable, but I don't know how to rule this out. And I don't know how to rule out the same statement for interval exchange transformations. So could it be that for almost every interval exchange transformation, for some permutation on 80 million intervals, if I look at the Ayiti along n factorial, 1/2 converges to 1/2 along the factorials. So that's somehow the absurdity of our ignorance. And so then the next is kind of a vague question, but I don't think it's studied much, and I think it's a very interesting question. What are the joinings between different IETs? So two typical random IETs don't have joinings, but can you build pairs of IETs that have interesting joinings? And in particular, what about an IET in itself? What kind of self-joinings can it have? And so also this second question about self-joinings of an Ayiti is related to a criterion of Veitch for when an Ayiti, for a process to be prime. That is, has no measurable factors, no simple pieces. And that's another open question about Ayitis, whether they're prime. And then, so along the lines of this full measure set of flat surfaces, but nothing explicit, I'm going to draw you a flat surface, the so-called golden L. This side has length 1, this side has length 1, this side has length √5 minus 1 over 2, and same with this side. Okay, so this is a very special flat surface. It has a large stabilizer, which is actually a lattice. It has a lot of nice structure. I think it's unknown if the flow in two typical pairs of directions on this are not isomorphic, whether or not there's some secret isomorphism between two typical directions. Okay, so thanks for your time.